All right, you guys ready to start? Section 2.2, we're going to finish that up today. We've been talking about sets in Chapter 2.
Sorry.
And today we're going to continue our discussion by taking a look at a diagram of how we can think about sets. The type of diagrams that are commonly used for these are called Venn diagrams. And they illustrate ideas in logic. You may have seen these used before. Sometimes, just like our truth tables, you'll encounter them in a critical thinking class or maybe our contemporary math class here. That's one of the things that my students in contemporary math just took a test on today, with some stuff with Venn diagrams. In the Venn diagrams, there's a few things to be aware of. The first one is called a universal set. The universal set is the set that contains all the elements that are being considered in a given discussion. So, for example, if the discussion were about, people I'm taking on vacation, we don't need to consider you guys because you're not coming on vacation with me, right? You're not elements of the set, so you wouldn't be in the universal. So it's whatever's being discussed or being considered in the argument. And then the complement is given a set F. This is all elements that are in the universal set that are not in set F. And our book writes complements with a bar on the top like that. There's a couple of other ways that complements can be written, so I'm going to show you them just because if you were to see them somewhere else, I don't want you to think that they are something different. There's just three common notations. This is one. This one's the one my contemporary math book uses. Kind of puts a accent mark, if you will, or a prime notation on the end of it. And there are some resources that will use kind of a superscript C for complement. So those are some other ones. We'll use the bar on the top. So the first thing I'd like to do is just draw a Venn diagram picture of the pieces that we've described so far. So when we're working with Venn diagrams, we're working with a rectangle. The rectangle represents our universal set, all the items that were being discussed or considered in the argument. And then when we have a set inside of that, we're describing it here as the set F, we draw it as a circle. Okay, so if we were looking at this particular Venn diagram, maybe you, as everyone here who's in class today, set F is all the females. Okay, so they would be inside the circle. And then the complement would be the area on the outside of the circle. Okay, in this case, it would be everyone who's not a female or who's a male. So we would have this sort of a picture of the yellow being the complement of our set F, which I will color in red. There's set F and set F complement. We'll do more with Venn diagrams. I believe it's in the next section. I don't think we're doing a lot more with it today. But we do have a few more things for discussion today about sets before we leave this idea. The idea of a universal set, right, all the elements being considered, can be used to create lots of things. So if we have this U as the set of all students at OBU, and A is the set of all those who are graduating, describe the complement of A. So what would the complement of A be with these descriptions? Yes, but I need a little bit more language with it. I don't need to be quite that specific. We need the at OBU part. Yeah, so this is the set of OBU students. Somewhere in there has to be the OBU students part who are not graduating. You can include more detail if you wish, but this is sort of the bare minimum that we need. Set of OBU students who are not graduating. Okay, any questions on that? So if we were talking about this set of students who weren't graduating, even as Marissa sort of described it, there's ways you can break it down further, right? We could talk about freshmen, sophomores, juniors, or something like that. Well, when we break sets down into sort of smaller components, those are called subsets. So a subset, description or definition says for all sets A and B, B is a subset of A, if and only if every element of B is an element of A. And the notation for this looks like kind of like a sideways U and a line underneath it with A. Sometimes I like to think about that sideways U looking more like a C to represent the word contained in as a descriptor or a reminder. This is telling me B is contained or it's inside of A. Right? It's embedded inside of A. So what we would expect if we were describing this set A complement right here and we wanted to break it down is that the set of freshmen would be a smaller set than just all the people who are not graduating, right? It'd be a subset of that. We also have what's called a proper subset. A proper subset, first of all, has to be a subset, right? That's how language works. You put a modifier on a word. It's already got to be a subset to start with. So for all sets A and B, B is a proper subset of A, if and only if B is a subset of A. That's the first deal. And then there is at least one element of B that is not in, at least one element of A that is not in B. And what you see is you see that same notation with that line is underneath that often means or equal to omitted. So there's something about this that's kind of like the notation when we say 4 is less than or equal to 5. We can also say 4 is less than 5, and we're removing the equal to part. Okay? Now notice the number 4 can be written as less than or equal to 5 or less than 5. I mean, both of those are true. But if I had this statement, well, it could be written here, I cannot write it here, right? This is not true. So if I can write it with that first notation, I have the possibility of writing it with the second one, but no guarantee. So I have students sometimes think about this as saying that this is a subset or it's equal to. That's one way to think about it, right? It's smaller than or equal to, it's contained inside of it, or it's equal to it, sort of that phrasing like less than or equal to phrasing. Whereas this one says it really is completely contained inside of it and it's smaller. Okay, it's smaller. So if you would imagine, so for example, my family. So if we looked at my family like this diagram over here, and we described this set F as the females and the yellow on there as the males, right? If we described it that way, we could make a subset inside of this that is the adult females or the teenager females or whatever, okay? But if you made the circle inside of it, the descriptive phrase, the females who are under 50, that'd be everybody. It would still be considered a subset, but it's a subset that's actually equal to the set already. It fits the definition, but it's sort of like, why? It's the same thing. Are you with me? So we can further define something, but if it doesn't actually make it smaller, it's not a proper subset, it's still just a subset. And you'll notice that I've sort of embedded these circles. This is the picture that we get for our subset notation here. So if we're looking for a set notation, Venn diagram notation for subsets, what we're doing is we're embedding circles inside of circles. Okay? So this is the set B that's a subset of the set A, kind of looks like a donut or something, and we have our universal set on the outside. Numbers of subsets. So you've got these things, right? So like the females in my family as an example, or the females in this class or whatever. And the question would be, well, how many of these subsets could I make? I mean, females was one of them, but males would be another one. Over 20 would be one, and under 20 would be one. Parents and not parents. And we could make lots of different categories. How many different groupings could we make? Well, that's what this is going on in this number of subsets part. It tells us that if we have n elements, right, my family would be 8 elements. This classroom is 2, 4, 6, 8, 10, 12, 14, 16. There's 16 of us today. We would be 16 elements. Then if we have 16 of us, then there are 2 to the 16th power, which is actually a fairly large number, different ways we could break this down into groups. Now, some of those groups would have like one person in them. That would be a subgroup. That would work, a subset. Some of those sets would have like 2 people in them. Some of those sets might have six people in them or 12 people in them. They'd still be a collection of people in the group that we're here in this classroom that's smaller than what we already have. So we have lots of ways we can sort of group people up. It's not infinitely many, but it's a lot. So when we're looking at a set of people, so we're going to do the math faculty because it's a small number. The set of all mathematics faculty members at OBU, there's 4 of us, Dr. Marsh, Dr. Tucker, Dr. Drake, and myself. And we want to know how many different subsets there are. Well, according to this definition, it should be 2 to the 4th. So what is 2 to the 4th? Don't know? It's 16. There are 16 different, smaller collections, or at least potentially smaller collections within the collection as a whole. And how many of them are proper subsets? Well, this description says all I got to do is to take one away. So if there's 16 subsets, then there's 2 to the 4th minus 1, or 15 proper subsets. So I want to write out for you how that makes sense in terms of those 4 people. And I'm going to use, I can use our last initials because they're all different. So we have Hans, Marsh, Tucker, and Drake. Okay? So one way to break us all apart is sort of like, oh, you've got each your individual office, your own little pod, right? Your own little space. So one option is that we have the set with just me in it, Dr. Marsh in it, Dr. Tucker in it, or Dr. Drake in it. So groups of 1. Sets of 1. We could also have sets of 2. So now we have to be more careful because we have to make sure we catch them all, right? So we can do H and M. We can do H and T. Or we can do H and D. And that's all the ways that myself, Hans, could be with other groupings, right? Because that's me with all 3 of them individually. But I could also have Drs. Marsh and Tucker. Or Dr. Marsh and Drake. And my last option is to have Dr. Tucker and Dr. Drake. Okay, we're going to get up to 16 eventually. How close are we? We're close, we're at 10. We're only missing 6. I have groups of 1, groups of 2. What would be next? Groups of 3. So I have a group of 3. So I have Hans, Marsh, Tucker. Or I can have Hans, Marsh, Drake. Or I can have Hans, Tucker, Drake. Does anybody know which one I'm missing? I am missing exactly 1. The one that doesn't have me in it. Marsh, Tucker, Drake. So what are we at now? 14. Okay, so we're only missing 2, right? And we're missing the 2 that seem to be the weirdest. The 2 that we're missing are the ones that have nobody in them. We talked about that last time. It's the empty set or the null set, right? Nobody in them. And we're missing the set that has all of us in it. So as far as subsets go, you always get these 2, the set that has nothing and the set that has everything. And then you get collections of things in between. Okay, so this problem didn't ask us to create this, but I wanted to create it for you because you will have to do some at some point yourself as well. All right, thinking about these relationships, an example, suppose you have a set about which you know that there are 63 proper subsets. How many elements would be in that set? So the proper subset formula looked like that, and it's supposed to equal 63. So if there's 63 proper subsets, how many subsets are there? 64. You can either do that with algebra, add 1 to both sides, or simply by reasoning through how they're related to one another. And if you wish, you can actually just do a little bit of trial and error with the number n to find what that n is. That's perfectly fine. If you want to factor this down, you can do that as well. 8 and 8, right? 8 is 2 times 2 times 2. We've got lots of 2's. In fact, we've got 6 of them. I know, it's amazing. 6 of them. So that n over here should be 6, because 2 to the 6th is 64. So this group would have 6 elements. But if you wish to use trial and error, that's perfectly fine. It will have to be a whole number, so it's easy to figure out usually. All right, we are going to do 2 problems back to back that look very similar. We've got example 7 and example 8. And if you compare example 7 and example 8, the only thing that's different is the direction part where it had the symbols. Number 7 says element or not an element. Number 8 says subset or not a subset. Okay? So there's no reason for me to create lots of examples because these examples work really well for both of them, so we're going to use them for both of them. Okay, so remember, element or not an element means it is an item that's among the group that we're talking about, a single item. So number 1 shows this notation, and what does that notation mean? A null what? A null set. In particular, my emphasis right there was on the word set. This isn't an element because it's a set. I don't care what comes next. Sets are not elements. Sets are sets. So this is not an element, not because it's not contained in what comes next, but because it's just not an element at all. It just isn't. All right, number B, which has the 15 in it, letter B has the 15 in it. The 15 is an element. The question is it an element of the things over here? Right? Is it one of those? So Preston's shaking his head no. Preston, you are very quick to tell me no. Can you tell me what's going on in that set on the right?
It's an odd number.
Okay, that's what the left is. What's described on the right?
It says x is equal to 2, and since there's no number you can multiply by 2 to get 15, that's not an actual number.
Okay, so the description on the right, you have to figure out what it's describing first. Okay, what it's describing on the right-hand side are even numbers. They're numbers when you multiply by 2, you get something, right? You multiply by something and you get something, and they're even. So everything that's on the right-hand side is an even number, and there's no number I can multiply by 2 and get 15 because 15's not even, right? Not a natural number anyway, and that does say I'm supposed to be in the natural number system. So this is why this one's failing. This is not an element, but it's not an element for a completely different reason than the first one. The first one was not an element because it was a set. The second one was not an element of what came next because it simply wasn't in that descriptor. Right? It wasn't satisfied by the description of what came next. How does C on the left side differ from B? And don't tell me it's a 4, not a 15. I know that. That's not what I mean. What's actually really different?
It's a set.
Yeah, those curly braces. So whenever we see those curly braces present, this is a set notation. So this is just like part A. It's a set. And if it's a set, it's not an element. And it doesn't matter what's after that. It doesn't matter at all because I don't have an element to begin with. Okay, so it's sort of got to pass, the litmus test of being a potential element. And it didn't pass that already, so we're done trying. Okay, how about D? Does it pass the first test of potentially being an element? Yeah, because it doesn't have the curly braces. Then we have to decide if it fits in this description. Does it fit in the description of what comes next? Yes. Question, Percy? You're good? Yeah. So we see D is actually a description where it's listed out. That's the listing method we talked about before. But it's this listing out of what does part B described. Right? Part B described the even numbers, and part D actually just writes them all out. A little easier to see, but it's actually the same set. So this one actually worked. It is an element. Now, in your homework, in your group work, you're going to have some problems where it's going to say to decide if it's an element or not an element, and you can just write them in, and that's fine. I would encourage you to write yourself a note and justify why, not necessarily because I'm going to count it right or wrong based on that for your homework, because it didn't ask. If you don't write it, that's fine. But if I ask on the test, I'm going to ask you to justify why. You're going to have to tell me how you decided. And your justification is as much a part of your answer at that point as your actual, like, it's an element or it's not an element. So at the very least, if you don't write it down, make sure you're thinking through that you really know why it does or doesn't work. Okay, we're a little bit familiar with these pieces now, but we're going to do a different direction set. The direction set now wants us to decide if it is a subset or if it is not a subset. So in order to be a subset, it must first be a set. Okay? So can you look at the list of A, B, C, D? Are there any of them that just aren't sets to begin with?
D and B.
Yeah, D and B. D and B aren't sets to begin with. So these are not sets, therefore they are not subsets. So then again, it doesn't matter what comes next. They fail because they fail to meet the description of what we're trying to describe, subset. They're not sets. Now, A and C are both sets. So now we have to actually decide, are they in fact subsets of what comes next? So subsets mean, and we'll go back to the definition real quick because it's been a little bit since we just looked at it. Subsets mean that the set on the left, all the elements in it, are also elements of what comes on the right. Everything in B has to be in A. Okay? So over here, the empty set is everything in the empty set inside the set that contains the number 0. Yes, it's a weird way of saying yes, but yes. I would write on your paper, if I were you, that the empty set, the null set, is always a subset of every set. It will always work for subsets. Now C is the number 4, right? It's the set that contains the number 4. So again, in order to be a subset means that everything inside of that set, there's only one item, is everything inside of that set also in the set that's on the right? Yes. And it's a funny description, but you can change it if you wish, right? This is just 3, 4, 5, and 6. And if we think about it there, then hopefully we see very quickly there is a 4 on the left. So there's a 4 on the right. So therefore, yes, everything in the set on the left is inside of the set on the right. All right. Anytime in mathematics that you see the word fundamental, it's really important. And it shows up periodically in different mathematics areas. We have the fundamental counting principle here. There's the fundamental theorem of arithmetic. There's the fundamental theorem of calculus. There's the fundamental second fundamental theorem of calculus. They like to use fundamental because they want you to know it's really, really important. So this is a very interesting one that you're probably aware of, but you might not have known that it was called this. It says that if we have two events, event M and event N, an event M, capital M, can occur in little m ways. An event capital N can occur in little n ways. Then event M followed by event N can occur in mn ways. So like I said, lots of M's and N's. But a really good quick example is the next one. Okay, so we're going to do an example of this. We're creating outfits. We have 3 shirts, 4 skirts, and 5 pairs of shoes, and we're assuming they all match, right? So what we're doing is we're saying that I have 3 different choices I'm making. This described 2, but it extends to using it for 3 or more. 3 different choices that I'm making. I'm making a choice of skirts, and how many do I have to choose from? 3. I'm making a choice of skirts. How many skirts do I have to choose from?
4.
And I'm making a choice of shoes, and how many shoes do I have to choose from?
5.
5. And the total number of outfits is the product of those values. 3 times 4 times 5 gives you 60. This creates 60 outfits. We'll do another one quite similar. We're going to go to the mall. You have 6 favorite stores in the mall, and assuming that you don't mind walking a lot around the mall, you could go to them in a variety of different orders, right? Okay. So the first one says you have only time to go to 3 of them. So we're only going to draw 3 placeholders because there's only 3 stores I'm going to. And we're assuming we're not revisiting the same store twice in this 3, obviously. That would be weird. We walk out, we walk back in. We're not going to do that, okay? So how many stores do I have if I first show up at the mall at this point to choose from? 6 of the ones I like anyway. And after I've visited one of those, how many do I have to choose from? And after I have visited both of those, how many do I have to choose from? 4. And the product, 6 times 5 times 4, 120. So there are 120 different ways that I could choose the order and go to these 3 different stores out of the 6 that are my favorite. Now, if I have time to go to all 6, I'll make a line for all of them. So it starts out the same. I have 6, I have 5, I have 4, and then what would I have? 3, 2, 1. And if you multiply these all together, how many ways do I have to go to my 6 stores? Shoot, this is why it takes so long when you go to the mall. 720 different ways to go to my 6 favorite stores in the mall. This might look familiar to you. It's not really part of our discussion right now, but I would be sad if I didn't actually draw your attention to it. If you've taken proportional and statistical reasoning in particular, Caleb has because he took it with me, what does that represent? It's a factorial. So 6 exclamation points, what it looks like. It's called a factorial. If that looks like Greek, just ignore it. You'll get there eventually. All right. I think that's it because we did the last one together already, like the real life example of an all set. Okay, so it's a good place for us to stop, and we will have time for our group work for section 2-2.